welcome back everyone. In this particular video, we are going to deal with a nice way to visualize general rotation of a body. The meaning of this particular title is that if you have any sort of a rigid body or any collection of point particles, we are going to see in at least how many ways, or at least in now minimum number of steps, how we can do the rotation of a body. That we are going to see in this particular video. And the thing that I'm going to deal with is the Eulerian angles. Hopefully I can do it. For that you need to stay tuned till the last. But if you stay tuned, I can promise you something good. Presented to you by MATHeSYICS Education. I, Akash Sarkar of that institution, is going to give you a quality learning for free. And without further delay, let's get started. Now, in this video, we are actually gonna see specifically with the Eulerian angle representation of general rotation of a rigid body. Okay, we're going to see the Euler angle representation. This is the thing that you're going to see. Euler angle representation. Now, we can see it in a rigid body, or in the simplest case, we can see it for 2 points. One of them is fixed and the other is moving. But I am going to deal with the most general case, that is a rigid body. Now, what I am going to make you see is this. Suppose I have any sort of a rigid body. Okay, this is the rigid body that I am talking about. Suppose I have a fixed point O over here. Okay, this is the fixed point O, and about this particular point, all other constituent particles of the body, such as this all, is having a general rotational motion with different radii, different velocities, and so on. Okay, that means after some time, this point which lies on the body will be at that position only, but all other points describing certain specific rotation will change their configuration to some other configuration, such as, for example, let me draw another arrangement such as this. This body and this body, the blue one and the red one, are the same bodies but in 2 different times. Let me consider this is the configuration of the body at t is equal to 0. Okay, at t is equal to 0, and this is the configuration of the body, let's say at t is equal to t. Okay, so in how many minimum number of steps can we do it? That is our main motto of this video. So let's start it. Always when we deal with something general, we start with something simple. In the similar way, we are going to start with the simplest possible case, and that is, suppose we have a ellipse. This is not looking like an ellipse, so let me rub it to draw a proper ellipse. Suppose here is a plane. Okay, let me label this particular direction to be x, this particular direction to be y, and from the corkscrew rule or right hand thumb rule, whatever you say, you know this must be the direction of the z-axis, and this is the point of the body which will remain fixed while the rotation occurs. Okay, the point O remains fixed. Now this is a plane. Okay, now in this plane, a plane, as you know, is infinite in extent. So in general, as a representative of plane, let me draw an ellipse on this plane. Let me draw an ellipse on this plane. Or how will the ellipse look like? Something like this. There is no specific equation of this ellipse right now that I need to describe the things that I want. So we will just see, this is you can also take a circle as well, no problem. But it must be at least an enclosed curve for your proper understanding. Now, instead of this entire thing, let me reduce it to something like this. So this is the ellipse, this is the x direction, this is the y direction, and this is the z direction. Okay. Now, see, this particular point O is fixed, I told you before. Now, since this particular point is fixed, let me pin it to earth. Suppose this is earth. Okay, this is earth. Let me pin it to earth. It is fixed. Now, as I pin it to earth, let me take a coordinate system and right away fix it to the ground. Right away fix it to the ground, penetrating to the surface of the body. Suppose this is a plane of a paper. You make a point, a hole in it, and you insert the coordinate system through it, and you pin it to earth. Okay, now the coordinate system is fixed for all time. Now let us take a similar set of orthogonal coordinates and do something like this. Suppose this was the initial set of coordinates which I have already fixed to earth. Now let me take the same set of coordinates, but instead of fixing it to earth, let me fix it to the body itself. Suppose I sellotape, with a sellotape, I fix it on the surface of the body such that when the body rotates, the coordinates also rotates. But at the initial instant when t is equal to 0, let me place it in a parallel, entirely parallel with the previous set of coordinates that I have fixed to the ground. The green one I have fixed to the ground. Now the black one that I have drawn just now over it is fixed to the body. Now as the body will rotate in space, this particular set of coordinates will also rotate. So the final representation of the body will be something like this. This was the initial representation with the axis like this, and this will be the, let's say this point is fixed, so the ellipse will something be like this. Okay, this is the line containing the fixed point, and about which means this is also a plane, this is also a plane, this is also a plane. This was our initial plane, this is our final plane, and always two intersecting planes intersect along a line, and the line of their intersection, let me give it a name called the nodal line or node in simple, but nodal line is the actual terminology. Node has many other meanings as well. Now this ellipse and this ellipse will intersect along a line. That's true. That's can be understood from this figure. Okay. Now, as you can very easily understand now, that from this point, if I draw the perpendicular on the rotated plane and specifically draw the orthogonal coordinates with respect to that, I will get this one. Let's say suppose x. Let me make the right hand rule clear. Okay, x, y, z, yes, correct. X dash, y dash, z dash. Okay. So after rotation, the orthogonal coordinates which I have fixed to the body has rotated like this. But the original coordinates which I fixed to the ground will still remain the same after a time t. And let me visualize those coordinates as this one, having the same origin, because choosing different origin will not help us. Because why? Because there is no translation of the body that we are considering. So there is no meaning in changing the origin. So these were our initial coordinates and these are our final rotated coordinates. Now in this video we are going to see the relation between them. Hopefully the diagram is clear to you, so I can proceed to the proof. Let me do something on this page, and in the next page I will do the entire thing. Okay, now Euler, what did Euler say? Let me change the pen. Okay, Euler said that, okay, how can we accomplish this task? Always refer to this figure. This is the ultimate figure that we are going to arrive after some rotations. Okay, so let me draw first our initial ellipse. Okay, suppose this is the initial planar figure. You can also draw a circle, I told you previously. Now after rotation, so this was our x, y, z axis. Let me call this axis x, this axis y, this axis z. Okay, now after rotation, after first rotation about the z axis, the x axis will come here, let's say x dash, and the y axis respecting orthogonality condition, that is 90 degree with respect to each other, will go there, and the z axis will remain as it is. Okay, so let me call this angle phi. This is the first Eulerian transformation. Okay, this is the first Euler angle. Okay, now as I do this, my figure remains the same, because after all it's an enclosed figure and it's a planar figure. So my figure remains the same. What changes is the direction of x axis and y axis. Also remains same is the direction of z axis. Now what I do next, let me go to the next page. Next, after accomplishing this task of rotating the coordinates, suppose this was my initial coordinates. Okay, this was my initial coordinates, this is my final coordinate after rotating by an angle phi. Okay, suppose something like this, x dash, y dash, and z remains the same. Now what I do, I rotate the z axis and make it come to this point. Let's say I rotate it by an angle theta. Now what I've actually done, to properly make you visualize, let me make use of another pen and draw a line. Suppose through the origin, this is the z axis, our new z axis, z dash. So the plane will be something like this. So the plane will be something like this, and initially what I call the nodal line, now the nodal line will serve as the axis of rotation. Everything now will happen, the rotation theta that I have just now accomplished will be occurring about this nodal line. Okay, you can understand that. Suppose you have a plane, you first of all rotate it, the z axis remains the same. I hope you can see it. First of all you rotate the plane, z axis remains the same. Okay, now you rotate the plane and the z axis, this is the direction of the z axis, becomes z dash. But about what line are you rotating? You are actually rotating about the line which is perpendicular to both z as well as z dash, which is nothing but the nodal line. Why? Because you know that a normal direction of the two plane, the direction of normal of the two plane is perpendicular to the line of intersection of both the planes. When two planes intersects, they intersect along a line, and that particular line is perpendicular to both the normals of both the planes. Okay. Now in that way, z dash is obtained from z by rotating about the nodal line. Now what has remained the same? The direction of x dash and y dash is just inverted. Okay, they have gone up. Now suppose I want to make another transformation which is possible. Let me change the color of the pen. Another transformation that is possible, that in this plane, when I have finally rotated the plane, I again rotate either the x-axis or the y-axis. Since we have already rotated x-axis, let's take into account the rotation of the y-axis. And now I will rotate about the z-axis, z-dash axis. So what I am going to do is rotate about this axis. Okay, I think it will be much more clear if I write down the steps. So what is the first step? In the xy plane, rotate about z axis. Okay, in the xy plane, rotate about the z axis by an angle phi. Okay, so this thing is accomplished. Second is, suppose in the rotated condition, what I'm going to do, I am going to rotate about the nodal line, that is the line joining the final two planes that would have occurred. Suppose in this figure, this was the nodal line. Why? Because this was our final plane, this was our initial plane. So the line of intersection of the final and the initial plane is the nodal line. I am not writing it explicitly again. Now this was an amount theta. Now finally, in the rotated plane, again rotate the x dash and y dash axis about z dash axis. That means now my plane is something like this, with this as the z dash axis, this as the y dash axis, and this as the x dash axis, right? Yes. So about this point I will rotate. When I rotate it, let me change the color of the pen. I rotate it, it becomes something like this. Let me say this angle is something called psi. Okay, so this amount is psi. So what are my three angles of rotation? Psi, theta, phi. These are the three Eulerian angles that we want to finally deal with. Okay, now how are we so sure that we have reached our destination? Let me go back to this page. Our destination was to frame this plane first of all, and after framing this plane, our intention was to orient the x dash and the y dash axis orthogonally in this plane. That we can only do if first of all we adjust the direction in which the z axis should be rotated by rotating the plane first of all, giving a twist to the plane, rotating the plane, and then again rotating. just like Rubik's Cube. Understood? Hopefully you can understand. Thanks for watching. Please to subscribe our channel. You know, sharing is caring. Watch our videos full for maximum utilization. From this video, it's absolutely inevitable.